In this flip, we will discuss the link between the thermodynamic concept of free energy and the concept of equilibrium. We have been using the terms spontaneous and non-spontaneous deliberately because there is a direct relationship between the equilibrium constant and delta G. The delta gives free energy change. Let's remind ourselves a few terms. Spontaneous process, it's a process that once started, occurs without outside intervention. Non-spontaneous process, it's a process that only occurs as long as energy is continually added to the system. When delta G is less than 0, the process is spontaneous. When delta G is equal to 0, the process is at equilibrium, neither spontaneous nor spontaneous. And when delta G is larger than 0, the process is non-spontaneous. We learned how to calculate delta G in general chemistry. One way was to use the formula of delta G equals delta H minus T delta S, where delta H was enthalpy of the reaction, T was temperature in Kelvin, and S was entropy change. Second way was to use the formula of delta G naught equals delta G of the formation of products minus delta G of the formation of the reactants. Usually you can find those delta G formations values in the appendix in the back of your book. The relationship under standard thermodynamic conditions is delta G naught equals negative RT natural log of K. You need to remember this formula. This is where we get the concept of 1 being this important value in the equilibrium constant. A value greater than 1 means that the natural log of K will be positive. So negative RT natural log of K will be negative, and a negative value of delta G means a spontaneous reaction. A K value less than 1 means that the natural log of K will be a negative number, and the negative RT natural log of K will be a positive value. Please memorize this relationship between free energy and equilibrium constant. When delta G is less than 0, K is large, therefore reaction favors products. If delta G is larger than 0, K is small, therefore the reaction favors reactants. Let's look at one of the examples. We need to calculate Kp at 25 degrees Celsius for the following reaction of delta G equals 134 kilojoules per mole. To calculate K, we need to use the formula of delta G equals negative RT ln of K. Rearrange equation and solve for ln of K first, which in this example is negative 31.4 divided by 8.314 multiplied by 298 multiplied by 1 over 1000 joules, and that should give us negative 5304. And after, when we get rid of ln, we take the e to the power of negative 5304, our final K value should be 9.2 to the negative 24. Does this answer make sense? Yes, since our G value is very positive, therefore the reaction is non-spontaneous. Thus K value should be small, which it is. In this example, using values from the appendix to calculate, we can calculate the value of G and then to calculate the value of K. We need to calculate the value of K for the formation of NO2 from NO and O2 at 298 degrees Kelvin. First, we need to calculate delta G for the reaction. In our review, we discussed that delta G can be calculated by using the formula of delta G of products minus delta G of the reactants. By plugging in the values of G formations from the appendix and multiplying them by corresponding mole number up front, we calculate that delta G equals to negative 35.5 kilojoules. This already should tell us that the K value should be positive. Negative delta G, reaction spontaneous, therefore positive K. Now we can calculate K by using the equation delta G equals negative RT ln of K, and our final K value is 1.5 to the power of 6, which is very positive, and it was predicted. In this flip, we discussed the link between the thermodynamic concept of free energy and the concept of equilibrium.